I think America's, sort of superpower as an organization or as a country has been its ability to iterate quickly, right? And hopefully learn our lessons and be able to stand these things up.
We are fast days.
Yeah.
I would agree.
So, with that, there are growing pains of trying to work in these new ways. And so I'm curious about, as you're, learning as you go, as you build out your own lab here with PNNL, as they're building out this much larger rack system and it increases in complexity. I'm curious to explore some of the challenges that come with kind of scaling up. So, one of them that I have spoken to folks about, who've been involved with organizations like Emerald Cloud Labs and Stratios, these sort of cloud wet labs that also had this dream of being able
with
to
Max Hodak last week. Okay. He's the original founder of Transcriptic that became Stratios. Yeah.
Great. So the AWS of science, where you could not, the person in their dorm room could be able to run an experiment. Yeah. Some of the challenges have been like, for example, scientists maybe aren't educated in translating their science into code or into specific protocols that can be, placed on these machines. And there's the economics of just capital-intensive, machines and trying to maximize uptime and so forth. So, what are some of the challenges that you think we're going to need to solve just as a country as we take this path for science?
Yeah, that's a freaking awesome question. So and again, I would say the major thing, like the most distilled version of the technology problem was what I showed you on the graph. It's like, get to the top right corner.
Get to the Waymo.
Yeah, and like even think about Waymo, right? So that boy, was their challenge hard, because the most dangerous thing I do every day is get in a car. So they had a huge bar, right? It was like worth nothing until it was safer, until they knew it could get safer than people. Yeah. It was worth $0. Nabil, right? And so
for something like a decade, I think.
Yeah, I'm just telling you. But if that had never got safer than human drivers, it's now much safer than human drivers. If it never got safer, it's a goose egg. It's over. Does that make sense? Okay. We're not in exactly that bad of a spot. Okay, right? People, if I'm not as good at some of the things at the lab bench, someone doesn't die or something. Okay, right? So I can kind of glide in there a little more easily. But let's just be clear. That is the core technical challenge. It is managing the variability with total automation. There is no doubt that if I had a lab that ran 24/7, where I could compress all the instruments into just the space that the robots need to move stuff around, not the space it needs for humans to wander, and it was running with a very small number of people instead of many people inside of it, which reduces EHS requirements, safety stuff, everything else, that will be dramatically superior on a cost basis, a time basis, runs 24/7, not 5 days a week, 6 hours a day or whatever, like a normal lab. It is an obvious winner economically, competitively with China, however you want to look at it. So it's really a question of, can you actually do that? Does that make sense? Okay. So then once you believe that, which I deeply do, then the next question is, what makes that hard? Okay, right? And we can talk about Emerald Cloud and things like that, which is a little more on a business model side. But let's first talk about what makes it technically hard. Okay, so what makes it technically hard? All right. First off, you need to support many different pieces of equipment all in one system. And the best way to think about all this is always to look at how a manual lab works. All right, so don't compare to a subway. That's the mistake actually people in the pharma industry and others do, because when I say lab automation, they say
liquid handlers.
Works out. Yeah, exactly. They're like, I got this. I know about lab automation. Let me talk to you about the system that screens my antibodies or something. And I'm like, yes, I agree. It's a great subway system. I think it's wonderful. You should keep it. I'm not trying to shut the subway down in Cambridge. I'm trying to get rid of the drivers. Okay, right? I want us to all be riding in self-driving cars. I'm not actually trying to replace the thing that goes to the same place every day because a lot of people need to go there. That's fine. Sure. Keep it. Yeah. Okay. Right. So I want to compare to the by-hand lab. Well, let's talk about what a by-hand lab looks like. All right. So you might have a room. It's I don't know. It's a 5,000 square foot room. There's 10 workstations for scientists to pipette at, and there's 60 different pieces of laboratory benchtop equipment in that room. Freezers, bench space, but then PCR machines and centrifuges and all the different stuff they need. And that's all in there available to every one of those, let's call it 30 scientists that work in there. All right, so that's a manual lab. I need to offer the same thing. What makes it hard to do that? First off, try putting 50 pieces of equipment on one setup. Okay, well now your little arm system, and it needs to be a little more complicated. You need a transport system too. You need rails and this, that, and everything else. Okay, so you gotta solve moving samples with high reliability among 50 devices. You also have to integrate 50 different devices. I can't have a person in there programming that thing. All those devices need to be controlled by my orchestration software that sits across the whole thing. So I got to solve that problem. All right, so you need to handle all 50. Now people have done that in the work cell. Biosero, high-res, we've obviously done thermo. The talking to the devices can get solved. 50 devices, 100 devices, every time that's been tried to do as a work cell, it's like a Frankenstein's monster, okay, right? And there's a bunch of these old story, oh, Lilly built this facility and, 20 years ago it was a failure, like everyone who's tried to put too many things on a old, inflexible system, eventually it like kaputs. Okay, so you have to figure out how to do that scalably. Okay, number two, you need to be able to do lots of different things at once. Because it's not the case that when you go in that lab, you lock the door behind you and you say, lab in use, no one else can come in. Yeah. But that's how the work cell works. Okay, right? If you're using it, I can't use it.
It's a lot of parallel processing.
Scheduling, right? And so it's like you and I using the lab together, right? And we'll see this on the lab tour, but I'll show you. We have a advanced scheduler to handle that. Okay, and then the third thing is it has to be easy. So, for example, if you want to do work at the lab bench, you don't have to write code. So you cannot write code to use the autonomous lab. Make sense? Okay. So that needs to get solved. All right. And so those are the big problems that you have to get over in order to make this thing work up here.
Right.
And the good fact about them is they're all engineering problems. They're not science problems. There's not like some unknown thing I got to discover about biology or something here. I just have to reduce these things to good practice, good UI for scientists, and have it be reliable. Okay, and I think they're all imminently doable. And we have made major headways on them, and then we can talk more about that. But the last point I'll make is the unique advantage we have at Ginkgo is we have two halves to our business. We do the automation and tools business where we sell these things to other people, but we also do, like we can talk cloud labs in a minute, but like we do sort of like research projects for other companies. So I have, deals with Novo Nordisk, Bayer Crop Science. We do like multi-year complex research work. So I have scientists here. The Ginkgo scientists are like the Waymo engineers 5 years ago in Palo Alto, not in the backseat of the Waymo, in the driver's seat, right? And they're there and they have their hands like right next to the wheel. And if it turns into a mailbox, they grab the wheel at the last second. Okay, that's my scientists on my autonomous lab today. I'm like, we're going to try to hit this month 30 simultaneous protocols. Jason, that's going to break the scheduler. Let's find out. It did break the scheduler. Great. Now the software team knows what breaks when you try to run 30 real science protocols at the same time, not some toy thing, and they fix it. Yeah. Great. And what's the next problem, right? And so by having like our own people here to like dog food it, we are moving dramatically faster than anybody else towards this goal. So I think we absolutely get there first, but those are the hard problems to solve. Many instruments on one system, parallelization, and ease of use by the scientists. Those are the three most important ones. There's a fourth, which is sort of like, how do you get the atoms onto the system? Okay, right, like that can't be as much of a project as using the system. So you kind of want to make that easier too. In other words, like how do you get the reagents on and your cell line on? Like how does that feel, again, to the scientist user? And that's it, we just knock those down. Nabil, like that's it, and then we're done. We're done with the benches, and science can actually start to move scalably.